If you haven't already watched the video on titration curves or pH titrations, you should watch one or both of those videos before you watch this one, since we will be talking about these titration curves and how they relate to buffers. There is an interesting region in each of these titration curves where the pH does not change by very much. So in this first curve, we can see that the pH remains around 2 pH units for quite a large range of strong base added into the solution. And for this one, the pH stays close to about 5 pH units for a similarly large range of OH minus concentrations that we've added. And then this one stays very close to 6 pH units for a similarly large range of OH minus concentrations. This behavior is called buffering. And this region is called the buffer region. A buffer is simply a solution that resists changes in pH when we add strong acid or strong base. Let's take a moment to see if we can figure out how this works. Recall that in the buffer region, we have both the acid ionization reaction to form the conjugate base and H3O+, as well as the base hydrolysis of the conjugate base, equilibrium, occurring, which forms the conjugate acid again, and OH minus. So because I have both the acid and the conjugate base in my solution in appreciable amounts, if I add strong base, it can react with the conjugate acid to use up some of the conjugate acid and make more A minus. Thus, the extra OH minus that I've put into solution gets soaked up by the conjugate acid and doesn't exist as OH minus in solution anymore, and therefore it doesn't contribute to a large rise in the pH of the solution. Likewise, if I add strong acid, it will react with the conjugate base that I have in solution, and it will make HA. And so any strong acid that I add will get soaked up by the conjugate base in solution and will not contribute to a large decrease in pH of my solution. And so one of the criteria, or one of the things that must be necessary to have a buffer solution, is that we must have both acid and conjugate base in our solution. We must have a conjugate pair in solution. You may have noticed that each of these three acids buffers at a different pH. So this first one buffers pretty well at a pH of about 2. This one buffers pretty well at a pH of about 5. And this one buffers pretty well at a pH of about 6.5 or 7. So why is it that different acids will buffer at different pHs? To answer that question, let's imagine what happens to my original solution of weak acid, HA, in solution. So I've depicted the HA as a blue conjugate base with a black hydrogen attached to it, and so that hydrogen is the acid hydrogen that's going to get donated to whatever base I have around. So when I start, I have basically just HA in my solution. When I add an OH minus, it's going to react with the HA by grabbing a proton and becoming water and leaving behind an A minus. By the time I get to the equivalence point of a titration, I have turned all of my HA into A minus by reacting with OH minus to form waters. And so at the equivalence point, all of my HA is A minus. So I should have the same number of A minus as I did HA to start with when I get to the equivalence point. That means that if I'm halfway to the equivalence point, so only halfway there, so if the equivalence point is here at about 40 milliliters, then halfway is about 20 milliliters. So if I'm halfway to the equivalence point, what do I have in solution? If I have all HA when I start out and all A minus when I get to the equivalence point, then halfway to the equivalence point, I must have half and half. So I must have half HA and half A minus. And that means that my HA and my A minus concentrations are equal halfway to the equivalence point. If I look at my expression for Ka, it's equal to the concentration of my conjugate base times my concentration of H3O plus hydronium divided by my concentration of acid HA. So if I am halfway to the equivalence point, then my A minus, my conjugate base, and my conjugate acid concentrations are equal. And if they are equal, they will divide out of this expression. And so I will find that Ka is equal to the H3O plus concentration at that very special point when I am halfway to the equivalence point. So we'll tag that with a sub 1/2 to remind ourselves that this is only true when I am halfway to the equivalence point. So if Ka is equal to the H3O plus concentration halfway to the equivalence point, then I can take minus the log of both sides of this equation, and I can say that halfway to the equivalence point, that the pH, which is minus the log of the H3O plus concentration, is equal to pKa, which is minus the log of Ka. So at this very special point, the pH is equal to the pKa. And each acid has its own unique pKa. And so halfway to the equivalence point will have a unique pH and therefore and will be related to the pKa of that acid. So halfway to this equivalence point is about 20, and the pKa of this acid is about 6.5 or 7. And so we can see that the buffer region is going to occur at a pH that is close to the pKa of the acid we are using. So the buffer region for any given acid will be at a pH that is within plus or minus 1 pH unit of the pKa of the conjugate acid.